Good morning, everybody. I'm going to show the weather balloon data is only in the last few years become good enough to be able to do the analysis that we do in this particular work today. All of the work before that wasn't possible until we had increased our ability to make measurements using balloons. So I'm going to be looking at these four main assumptions, which are the bedrock of the current climate theories, and check with this new higher quality weather balloon data to see if this actually works out. So I've divided the talk into 6 different sections, so I'll start with the first section, which is just dealing with what weather balloons actually are. So from about 800 regions around the world, every day a weather balloon is launched into the atmosphere, and they do it at one of 4 different times. It's either midnight, 6 a.m., noon, or 6 p.m. Greenwich Mean Time. So it doesn't matter what the local time is, they're all launched at these Greenwich Mean Time times. And so this allows, so what you get when you do a weather sounding is you get, when you looked at the data for this particular weather sound from Valencia Observatory in Ireland, and I'll explain why we use this particular one later on in the talk, but you have the identifier telling where, when, and how much data was collected. And this green one here shows you the actual measurements that are made. So it's pressure, height, temperature, dew point depression, wind speed, and direction from the north. Now, I've converted all of these into SI units. It's not they're the standard units, and it's easier to do an analysis in them. So this is the full record for that particular weather sound. So that basically is the first section. Now, in the next bit, I just want to introduce 5 concepts which I'll be using in the rest of the talk. It's not a complete history of thermodynamics at all. So the first thing is just to tell you what the thermodynamics is not as complicated as you think. It's basically learning to turn heat into motion. The thermo came from the heat bit, and the motion that gave rise to the dynamic bit. So that's just how the name arose. So, the big idea behind thermodynamics was the concept of energy. And the first law of thermodynamics simply said that energy couldn't be created or destroyed, but we have all the different types of energy, and they can be transformed one type into the other. So all that I want you to do here is just what's called a barometric equation. And this says how the pressure is related to the height. So all that I want you to remember is the pressure is an exponential decay function with height. So as you increase the height, the pressure decays exponentially. And it was derived using a concept called isostatic equilibrium. So all that says is that the difference in weight, or the difference in pressure between one height and another, is equal to the weight of the air in between. So the other concept I do is this is the ideal gas laws. So when they were deriving the different laws and combining them together, all the experiments were done with air. It was the only gas that they had available at the time. And so obviously, since the ideal gas laws were determined using air, air is an ideal gas. So the next thing that I want to point out is this is the most difficult bit to get across. It's a concept called thermodynamic equilibrium and the equation of state. And maybe if I skip to the next slide, I might be able to explain it better. Basically, the very first, the combined gas laws were the very first equation of state for a system. And what the equation of state simply says, I get onto that in a minute, but the normal way that you see the ideal gas law written down is in this form, PV equals nRT. That's the energy form. But you can just rearrange this, it's just a mathematical rearrangement, and write it in what's the molar density form. Now this contains the exact same information as this here, it's just presented in a different way. So what does an equation of state tell us? Well, if we look at the energy form here, the units on this side, the equation of state is an equation that relates all of the state variables to the system. So you have pressure, volume, number of moles, temperature. So what it says is that if you want to heat the system, whatever it is, a kilogram of air or whatever, you'll have, if you put heat into it, not all of the energy goes into heating the system. Some of the energy is transferred into work energy. And equally as well, if you get the system to do work, the temperature of the system will drop. What the equation of state doesn't tell you is how much energy you have to put in to cause the system to heat by a degree, for example. For that, you need to know the heat capacity of the system, and that's something you have to measure separately. Each system would have its own heat capacity. The other thing is, I could take a kilogram of air, put it into a box, and lift it up 100 kilometers or 100 feet in the air, and it would have potential energy. But the equation of state, because it would be a system like, it doesn't tell you anything about that potential energy. So there are limits to what an equation of state can tell you. The last thing that I wanted to tell you, what I should emphasize though is, what do we mean by thermodynamic equilibrium? Basically, what it says is if I put heat or something into a system, the energy will be distributed among the different types of energy that can be housed in it. And when all of those have settled down so that they then obey the equation of state, it's said to be in an equilibrium position. So the thermodynamic equilibrium is when the system obeys its equation of state. So if a system obeys an equation of state, it's in thermodynamic equilibrium, and if it's in thermodynamic equilibrium, it'll have an equation of state. So they're just two sides of the same coin. The last thing that I want to go on to is the lapse rate. So if you go up in the atmosphere, it gets colder as you go up. And up until about 30 years before I was born, everybody thought that it would drop off at 6.5 degrees right out to outer space. And then at the beginning of the 20th century, they started to be able to launch balloons, and then something strange went wrong there. So the next bit here is a talk, is on a paper that we had published last May, at the end of last May, about 5 or 6 weeks ago. This paper was only published, or was only possible due to a very high quality ozone series of measurements that were put out by NOAA. But before I get into that, I want to go and talk a little bit about the ordinary radio sound. But the main part of this section is based on these papers here, and I'll get back to them in about 3 or 4 minutes. But if we look here at that radio song that I gave you at the beginning for Valencia, if we plot the temperature values there, and if I use height as the vertical axis, this is the value, the shape that we get. If instead I use pressure, you see it gives us a different shape. This is very useful in that it shows us the lapse rate falling off at the measured one here is 6.8 degrees Kelvin per kilometer. But this one gives you a better idea of the amount of atmosphere that's involved. So you can just look here, and from the pressure you can see that two-thirds of the atmosphere is in the troposphere. So this is what happened when they launched the balloons. They found that instead of the lapse rate continuing on up, it came to a tropopause. But I'll just skip on. This is showing that self-same sound and showing the altitude and the thing, and this is showing the lapse rate. So you can see the lapse rate. This was when they started launching the balloons that this surprise occurred, that the temperature didn't continue to fall off into outer space. And I just want to show what happens when you. So there's a reason why I'm using both vertical scales, either altitude or pressure, and it'll become obvious a bit later. It's got to do with the barometric equation earlier on. If I use pressure, you can see the lapse rate curve falls off exponentially. And you'll find that with some of the things we're talking about, things that are a straight line with the pressure become curves when I look at the altitude. And I will nip back and forth between both methods to help illustrate the points. So here's one of the things that I'm saying. If we, instead of using the energy form of the barometric equation, if we use the molar density form, the molar density, which is D here, is very easily determined from your weather balloon data. It's a simple equation. And if we plot the molar density, what we find is we get two straight lines. They stop at the tropopause. So this is just showing, and this is just showing these straight lines. So what happens here is we can see this straight line. If I just do a linear least squares fit to see how good the actual data is compared to a straight line, you see a factor called the R-squared factor. If it's a perfect fit, that'll be 1. And this, we can see, it's not quite a perfect fit. There's a little area here that's slightly bit different and here, and I can show you those later on. But the bottom line here is that the molar density is showing that the troposphere obeys an equation of state. What you can see is that the troposphere obeys an equation of state. So I'm just again here showing this in the altitude. You can see that the equation, the molar density equation there, would be an exponential function until you hit the tropopause, and then it becomes a different exponential function. This line here at the tropopause, this is also a linear with an R-squared values of 0.99. So what we can say here is the first bit is that the tropopause obeys an equation of state and is therefore in thermodynamic equilibrium. And above the tropopause, we have another equation of state, which is also means it's in thermodynamic equilibrium. Therefore, the assumption the atmosphere is not in thermodynamic equilibrium is false, right? Now, going back to the paper we published, which is the main part of this thing here, This was only possible because in 2016, NOAA launched a series of ozone sondes from these 8 locations with very high precision measuring abilities in them. They were able to take a measurement every second. So that previous one that I had from Valencia, there was 103 readings taken right up to the stratosphere. In these sondes, they had over 4,000. They were taking a reading every second or every 5 meters. So this allows you to do derivatives and other types of mathematical analysis. You can do rates of change because the intervals are very short. There was only the 1 year that all of these 8 stations operated. The very high quality data, but again, only once a week was all they launched them. But when we look at the definition of the tropopause that was put out in 1957 by the WMO, they said that the tropopause was when the lapse rate suddenly went from 6.5 degrees to less than 2 degrees per kilometre. But they put in another proviso. This was the definition that they put in of the tropopause. And they had 2 clauses in it. One was the temperature had to drop below 2 degrees per kilometre, and it couldn't exceed that for the next 2 kilometres. But with this new quality, high quality data, we were able to come up with 4 different new ways. So when they made this definition with the data available, it was probably the best they could come up with. But we now, with these ozone sondes, they were making very precise measurements of water content, ozone content, as well as temperature and pressure. So we were able to find that 4 independent things happened at the tropopause. First, when you hit the tropopause, the atmosphere becomes dehydrated. The concentration of ozone increases. The change in the molar density, which I've just described, happens. And then a strange thing is, instead of the temperature pausing, it now begins to oscillate very wildly. So, I'll show the results from all of the 8 stations, but just to make it simpler, I've just taken 1 from the tropics, 1 from mid-latitude, and 1 from the Arctic. And the first thing you see is with the molar density. By the way, we are the first group to ever consider the molar density form of the equation of state and apply that to measurements of the atmosphere. Nobody else has done this, which is quite bizarre. And therefore, nobody has realized that this phase change occurs. So what you can see is in the colder regions, the phase change occurs lower down. For convenience, I've only taken the top half of the atmosphere for this. So you can see that 66% of the atmosphere is in the troposphere. In the mid-latitudes, it's around 75%. In the tropics, it's 85% to 95%. And so we came up with these, looking at these data, 4 new definitions of the tropopause. Now, these 4 new definitions, rather than go to, but I will illustrate them graphically for you. So the first one here is the one in the tropics in Hawaii. So our definition says that if you look at the rate of change of temperature, as soon as it changes, goes through the 0 axis, we define that as the tropopause. But we also say that the rate of change, either with pressure or temperature, starts to oscillate wildly. So this is our new temperature definition. And if we look at the mid-latitude one, you see the same rule applies. Here's our 0 axis. As soon as it crosses that, it starts to oscillate wildly. So that we're saying is another tropopause location. And then when you go to the Greenland, you can see the exact same rule applies. So this rule applies to all of the tropics. It's just the location of the tropopause varies. This is very surprising. Why is it that it's not a pause? The temperature starts to oscillate wildly instead of pausing. It wasn't what we were expecting. So I look at the next one, the molar density. We define that as where the phase change occurs. And again, where the rates of change start rapidly varying. And then when you look at sorry, I'm very bad at doing this today. Sorry, there's the molar density. Again, there's a big delay between when I press my finger and the slide responds. Don't know why that is. I might change from the button, or from the mouse to this. Okay. You can see, again, this change, the phase change is, the behavior in the rates of change is similar. And again, when we go to looking at the water content, this time it's the reverse. In the lower end of the atmosphere, there's huge oscillations in the water level, but as soon as you hit the tropopause, it drops down below 50 parts per million, and the rates of change go to zero. It's essentially dehydrated. And again, for each of the stations, you can see. Now, on this scale, it's not that hard to see, or it is very hard to see. But if I magnify this up, the transition is clear enough. But this is just for illustrative purposes. Here in the Arctic, it's a very dry region, so you don't get much oscillations down there. Now we come to the ozone one. There is ozone in the troposphere. It's small. It's about 0.1 parts per million. But as soon as you hit the tropopause, the ozone level starts to increase. Also, the rate of change in the troposphere is fairly steady, and then the ozone starts to oscillate wildly when you go above the tropopause. So this is again showing the mid-latitude one, and again showing. So what you can see is these 4 new ways of detecting the tropopause work for all the climatic zones. The behavior is the same. It's just where the tropopause starts that's different. So how do these 4 new ways compare with the standard WMO way? So this was for all of the stations. The old way that the WMO defined it, you can see is these grey little dots here. And our 4 new ways are reasonably well correlated. They all do a roughly similar sort of analysis in that if we look at the tropical ones here, the tropopause occurs in the top 10% of the atmosphere, whereas it's down you've only 60% here in the Greenland way. So they are all roughly similar. But I'll just go back to those 3 again. What you can see is that the WMO's definition seems to read slightly higher. And you'll see why in a second. So I'll just take this particular date here and compare it because I have the analysis done on that one. So this is the one I was showing you earlier of the 25th. So the WMO's one is the grey one there, and then our temperature one is the green one. They're slightly different. And so this was the one that I showed you earlier in part of that mess that I presented. So here is using the pressure curve, and the stratosphere is quite small. So I'll use the altitude one because it spreads it out and it's easier to look at. And I will just hone in on just one of the rates of change. It doesn't matter. So this is the temperature, right? And this is the rate of change. Now, from our temperature, our definition of tropopause based on temperature will give you this red line here. So I'll just amplify that up. So what we're saying is, as soon as the rate of change crosses the zero line, that's the start of the tropopause, and when it starts to oscillate wildly. And so you can see the rate of change here was relatively smooth, then it crosses the zero line and it oscillates wildly. The WMO's definition says that the temperature drops off as soon as it gets less than 2. Well, that's fine, it's getting less than 2, but it has to stay that way for 2 kilometers. And this is only half a kilometer, and then it starts going back to 6 again. So they can't use that. And it's only here that it finally reaches their criteria. So you can see it's a rather ad hoc definition. And so you can see why it gives the slightly higher readings than our 4 independent ones do. You can see it's not capturing the sudden change in behavior of the rates of change or in the temperature itself. Another definition that they use for tropical temperatures is the cold point. So in tropical regions, they say the tropopause starts at the coldest point in the atmosphere. And so this is a tropical station, and the coldest point there would then be that one. You can see neither of these former ones are very good. So thanks to the new set of data that we were able to get from those ozone stations, we have been able to develop a new definitions for the tropopause that are independent of each other. And now what we've got to do is say, well, okay, what can we do with that? So, by the way, those papers, that paper that I was just discussing, that was just published 6 weeks ago, but it's available for download free. So let's look at the applications of these new results to see, can we go back and look at radiosondes? Obviously, the ozone sondes have an ozone measurement and the radiosondes don't. So we can't use the ozone definition. But since about 2008, the new developments in measuring dew point depression have become so good that we can now actually, I'm going to look here at these these radiosondes from Valencia. They started launching a high quality radiosonde on the 15th of June, midsummer, for nearly a year and a quarter. And so, but the difference between these is that they were launching these every 4 times a day, whereas the ozone sondes were only once a week. So this allows us to look at more what's happening on a continuous basis. So what they had in these particular radiosondes was a way of measuring the dew point depression right up to the stratosphere, from ground to stratosphere. And so we now can do that to within a 2% accuracy for over this range from where. So what the dew point depression says is that if there is 0 dew point depression, it's raining or it's cloudy. The condensation's already taken place. If it's above that, it doesn't. But the drier the atmosphere is, the greater is the dew point depression. So if you have, it says, the dew point depression says how much you have to drop the temperature in order to get it to condense. And you can see in the tropopause here, it's 40 degrees. It's dehydrated. A bit like I'm feeling at the moment. Yeah, okay. So here is looking at that very first sonde that I showed. Thank you. So what we look at here is the standard, or our location of the tropopause using our new definition for temperature. Here's our molar density one, and here's the dew point depression one. So again, as I showed you earlier on, this is almost in thermodynamic equilibrium except for this tiny little dot here, which I said I'd get back to, and I will. But the first thing that I wanted to do is to look at the 4 radiosondes that occurred on that day. I picked this one because it was the first day that they launched this type of radiosonde. So what you can see is this is the 15th, so 0 means that that's the midnight one, 6 is the 6 a.m., 12 is the 12 noon, and 18 is the 6 p.m. And within the tropopause, or within the troposphere, they all have roughly the same lapse rate, except in this little areas here you get these differences. And these are what's called the boundary layers, where rain events occur. So I'll just magnify that up for you. And you can see how our new definition of what's happening at the tropopause, you can see the tropopause, or the lapse rate, decreases until it hit the tropopause, and then the temperature starts to oscillate wildly. So in our derivative ones, we could see that, but you can actually see here the physical things. And this is only over 6-hour intervals, but the zigs and zags are not coordinated at all. They're random back and forth to each other. I'll magnify this a little bit more at the actual tropopause. So what you can see here is at the coldest time of the night, when the sun goes down, it starts to get colder, and so the air temperature drops. And then as you go through the day, the air temperature goes up. But what's interesting is that the air temperature goes up uniformly over the whole atmosphere, not in a random way. So as the atmosphere heats up, it does so uniformly from top to bottom. And the other interesting thing is that the hot days, the days at the hottest time of the day, well, not the hottest radiosonde of the day, I should say, at that time, the tropopause occurs at the highest level. And so on the hot days, the temperature, the tropopause is higher, but above the tropopause, the temperature is colder. And in the colder times of the day, the tropopause is down lower, but above the tropopause, it's hotter. So they're anti-correlated. And so what I did here was I just simply said, well, let's just take the hottest radiosonde of the day and say run them for the next 5 days to see what happens. And then this is a strange sort of thing. This is, remember, is above the clouds. I'm talking at mid-atmosphere. So, and it's in the middle of the summer, so the amount of solar energy coming in is the same. The daily heating can't be what's causing this because it's all at the same time. But again, the same rules apply. The hotter days have the higher tropopause and the coldest stratosphere, and vice versa. So I've just summarized these results here. But the key thing to notice is that whether it's from during the day or from day to day, that the whole atmosphere behaves in the same way. It's so what I just want to now do is concentrate on this lower bits, the boundary layer, and some of you might find this interesting. I do, but then I'm strange. So this is including the dew point depression for the 5 stations. Obviously, it's a mess, so I've eliminated all except the last 2 to try and show you what's there. But so this is the last 2. So what you can see here is that the dew point depression drops to 0. So that's a rain event. And what happens is, above the clouds or the rain, the temperature gets a little warmer. But it doesn't last for long before it starts coming back to the same lapse rate. And again, here's another dew point depression, another rain event, and it gets warmer. But within less than a kilometre, it's returned to its old regime. And so those little dips that I was saying, they are showing you earlier, they caused they to be not perfect, were little rain events. Here is another one. Again, you have the dew point depression. Now, this was probably a thunderstorm. Thunderstorms take on average about 30 minutes to develop. And you've experienced them here over the last couple of days. You get a big downpour of water and then it stops. But bear in mind that the balloons only travel up at about 5 meters a second. So to get to these particular places takes about 15 minutes. So this might have been a whole series of rain events, but by the time the weather balloon reached these locations, they had fizzled out. But what you can see is in the temperature record, they still have, for the 10-15 minutes, the warmer bit above the cloud. So I'm assuming this was a cloud event as well, and so on. But again, what's interesting is that the deviation of the temperature above the cloud is only short-lived. So where are we now? Okay, so this is just showing the relationship between the temperature at mid. I'm taking the mid-atmosphere as a temperature, and this was just showing how the colder it is, the lower the tropopause is. Mid-latitude, it's warmer, and so on. So what I did was I took the first month of this set of data, and I got the temperature at mid-latitude. And so what I've done is plotted the position of the tropopause with respect to the mid-latitude temperature. And what you can see here is that if you do a least squares fit, the R value is 0.75. What that means is it's accounting for about 75% of the behavior. So this is just plotting the same data here, but instead of plotting one against the other, I've plotted them spread out over time. And what you can see is the orange one here is the height, and the green one, the blue one is the temperature. And you can see the behavior is similar. So if I'd ever take the mid-temperature and plot that against the temperature at the tropopause, they're anti-correlated. So what can we conclude from this? Okay. The second assumption that we looked at was that heating or cooling causes buoyancy forces, and the implication was that this causes convection. But from our latest research, we've seen that the atmosphere heats up during the day. For the entire atmosphere heats up uniformly. And so if you heat a parcel of air at, and if in order to create buoyancy forces, you have to leave the rest of the air around it still cool. If you heat a parcel of air, but all the air around it is heated proportionately, then there are no buoyancy forces. It just sits where it is. And so what we're saying here is that because the atmosphere heats up uniformly, then you can't rely on buoyancy forces for convection and so on. Anything based on that just won't work. So now, what is the cause of, so this is a paper that we published 2 years ago, and this is where it was, and it's really going back to looking at why from day to day at the same time of the day is the temperature different, because the sunlight and the clouds have nothing to do with it. And so the current model that people have of how the atmosphere behaves was based on Hadley's observations and trying to explain the trade winds. And Hadley's proposal was that if you heat the atmosphere at ground level, sorry, I'll just try this. Yeah, I was trying to. There we go. Okay, so what you can see is he says that the atmosphere goes towards the tropics. It starts to heat up, going as the ground gets heated up, and then it rises up at the equator. And he didn't say anything about Hadley cells. He didn't know about the tropopause. He just simply says that there was convection rising up, and then it travelled north and cooled, and then came back down again. And he got this circulation pattern based on the rising air. So I'll zoom in, and then the Farrell cells. So this latest one that we're looking at, when they discovered that the tropopause was there, they modified the Hadley cell, said is that you can move along the ground, it gets hotter, it rises, but it can't rise through the tropopause because that's hotter. And so it travels north, and then it cools down, and the circulation pattern goes like that. Well, now, from our looking at molar density, we realized that we're able to actually determine the density, the actual density at any point in the atmosphere. And so also from the weather balloon data, so we can determine something which is called the mass flux. And so what the mass flux is it measured the mass of air flowing through a square meter in any direction. So if we know the wind speed, we can resolve that into its north-south. If we know the speed and direction, we can resolve it into its north-south component and its east-west component. And so if we go back to this explanation, we should be able to check this. Because if it's correct, if we send a weather balloon up through the middle of this, we should see the mass flux going in this direction and then changing and going northwards in this direction. So that's what the mass flux curve should look like. And then the Brewer-Dobson circuit, I actually hadn't explained that. The Brewer-Dobson explanation is for why the tropopause is warm was they said that the tropics UV sunlight is absorbed by ozone, and that helps to heat the tropopause, and that's why it's warmer. But then people pointed out that why is there more ozone in the Arctic in the winter when there's no sunlight at all? And so to explain that, and very little in the tropics where it only occurs very high up. And so what they said was that the ozone is generated by a mechanism called the Chapman mechanism. I'll get back to that in a minute. But that it's then there is a Brewer-Dobson circulation current flowing all the way to the north, or to the poles, bringing all this ozone with it, and that's how it builds up. But again, we should be able to see this circulation should be like that in the tropopause, if that's the case. But nobody has actually physically determined the Brewer-Dobson circulation. They've used the ozone as a way of measuring it, a sort of circular logic. So this is just showing how we determine for radiosonde the mass flux. I'll go on to what we actually got here. So we took these stations and we did the mass flux on a daily basis. I'm just plotting here the 31 point moving average, because otherwise it would be oscillating too much. But except at ground level, in Iceland here, I don't know what was going on here, but you can have things like glaciers melting or various things. But except for ground level, when we go above the ground level, what we find is that, just magnify that, is that all of the mandated levels all oscillate back and forth on a daily rate at the exact same. Sorry, wait till I see if I can do this. Yeah, so what you can see is all of those colours are going back and forth at the same rate. You don't have a continuous circulation in one at the ground level and another one at a higher level. Instead, all of the pressure, mandated pressure, for this, the tropopause would be about 300. But right from the ground up into the stratosphere, you have this oscillation back and forth. Instead of a continuous circulation, you have the atmosphere is acting like a big pendulum moving backwards and forwards. That's on a daily basis. And then if we go and start looking at averaging it over the entire length of time, so I'll just get rid of some of this here. What we see is here in this particular station, averaged over the 5 years, we have this difference, but it's the wrong direction. So instead of blowing from the high latitudes at ground level, it's going in the wrong direction. And when we look at the Brewer-Dobson pattern, again, that's going in the wrong direction. And then some of the stations don't have anything at all. Now, this was the paper we published there 2 years ago, or whatever. But since then, we've been looking at all of the stations. We've had a colleague, Adrian Bratt, has been going through each of the stations and seeing what the effect is. And what we're finding is there's absolutely no evidence for any of these circulation patterns at all. So if you do correlations on a daily basis, you see the entire atmosphere gives you a positive correlation. If they were going in circulation patterns, you'd expect to see some negative correlations, and that's not what happens. So what we can conclude from that is that there is no evidence for the Hadley cells, Farrell cells, and polar cells. Instead, the evidence seems to show that the entire atmosphere acts like a giant pendulum, moving one way, a couple of days later moving back and oscillating back and forth. So that is the end of it's not the end of the talk, the end of the solars, or the cells sort of thing. So this is, how much time have I got left?
About 3 minutes.
Okay. Well, okay, I'm only demolishing the last one. So here we go. Okay, this is based on work that we did in our, which we published as working papers in our own open OPRJ journal. So they're available there for you to look at. So we're looking at the atmospheric ozone. Now, do you notice the way we seem to have a phase change occurring at the tropopause? Phase changes are not unusual in science. If you're want to describe gaseous water, you will use the standard gas laws. That's the equation of state. But if you change to liquid water, you have a different equation of state. So when you get a system going from one equation of state to another, you get a phase change. We've put forward the idea that oxygen condenses down into multimers of oxygen. In other words, instead of being a chemical reaction, though, it's what's called a van der Waal type forces. So just to illustrate, there are different allotropes of oxygen. This isn't as far-fetched as it might initially seem. So what we have is, normally ozone is a blue gas. It has a half-life of about, at normal temperatures, of about a day, but at cold temperatures it can last for about 100 days. The tetramer or dimer of oxygen, that's been proven to exist in trace amounts and has a binding energy of that amount. There is, if you take ordinary oxygen and compress it down at room temperature, it'll form what's called red oxygen. And that has a tetramer structure, and it's something like this. So the oxygen molecules are based like a little square, and that's what the red oxygen is. And then when we look at liquid oxygen has an evaporational, it's a binding energy of about minus 6.4, and it's blue in color, it's sky blue in color. Now, why is ordinary oxygen colorless, and then when it becomes liquid, it becomes blue? And the reason put forward for that is that some multimer of oxygen, maybe a tetramer, absorbs red light. But red light is over 100 kilojoules per mole. So that will involve, from a chemist's point of view, electronic transitions. So it's no longer just behaving like a van der Waals molecule. Now, that is... the reason I'm saying this is that when we come along, and so what I'm saying is at the tropopause, if you get these van der Waals multimers occurring, you'll get a condensation. And so that's why we're getting a change in state. Instead of being O2, it's O8. But just to conclude here on this, so when we're looking at the ozone, we have the Chapman mechanism says that it's formed here in the tropics and it travels towards the poles, but our analysis of mass flux, and again, we were the first people to actually look at mass flux. Nobody else, it hadn't even dawned on them. They looked at the speed, but they never looked at the total mass. If you're looking at something that's only 1/10 of the mass, but it's traveling at twice the speed, it's still not delivering the same amount. So our analysis shows, therefore, that the Brewer-Dobson thing doesn't exist. But what you'll find is here, I want to do just this last bit. The ozone in the troposphere is very small, but it's there, and the explanation for it is that it's due to smog and pollution. So if we look at the summit in Greenland, Greenland is the largest island in the world, very small population, 50,000. The capital is about here, 600 kilometers away. It has 2,000 in it. And this station is, if you look, it's 3.2 kilometers up in the air. So it's about as far from smog as you can get. It's probably the most smog-free place in the country. So what I did was I took the summer and nighttime molar densities, and I looked at how they were behaving. There's the temperature one. And again, you can see the change in temperature. But what I noticed is that there was a deviation from the straight line molar density here. And also, there was a tropopause here in the winter. So we have these tropopause here, this change of molar density here, change of molar density here. And then I said, well, what happens when we look at the ozone? And lo and behold, when you look at the ozone, yeah, it increases there, but down here it increases in the Arctic winter when there's no smog and no sunlight. And also, it becomes suddenly dehydrated, the water drops off again. So our four analyses that we used here, we could apply here as well. So that says that the Chapman mechanism couldn't account for it. I've just magnified it here. Sorry. I just magnified it here. You can see. You can see the temperature pause. You can in the winter. It's not there in the summer. You can see the ozone increasing, and then you can see the dehydration occurring, no water vapor. That doesn't happen in the summer. And that was one time, but you can see there's an example of it happening again. So our proposal for the formation of ozone is not based on UV light or anything else like that. What we're saying is that if you have tetramers, and if they absorb red light, they become excited. If they collide against each other, they'll have enough energy to form ozone molecules, and independent of UV light, and they don't need to be formed in the tropics or anything else like that. They're formed in situ. Now, an interesting point, just the last bit. So there you go. Balloon data shows that the net mass flux above the tropopause does not support the Brewer drops in circulation pattern. And the localized increase in ozone at ground level in the winter summit in Greenland is not due to smog and can't be created by an Chapman mechanism because there's no UV light. Right, so that's all of the four demolished. This is just, if I've just one last thing to do. Why is the sky blue? Well, according to Lord Rayleigh, it's because the blue light is scattered to a bigger extent than is the rest of the light, and so that's why we see blue. But then at night, in the evening as the sun is setting, the red is scattered more. But the problem I have with that is that we know that if you scatter light with, say, rain droplets, you get a rainbow. So why don't we get rainbow sunsets? Why is it always just red sunsets at night or in the morning? Now, if our idea that multimers are formed in the stratosphere, or in the troposphere, the tropopause, if they absorb the red light, then the sky will appear to be blue. But the red light will be re-emitted. But because it's re-emitted in all directions after being absorbed, you don't see as much of it coming along the path. But if you go and the sun is setting, the blue light is going off at an angle, but the red light will be emitted towards you. So if we're right, you'll only get red sunsets. So it's an alternative explanation. I won't bet any money on it, but I'm just saying. Right, that's it. Sorry. I wasn't too far over, was it? I would have liked to have time for some questions, but I will be around for the rest of the time. So if anybody wants to come and query me on anything or tell me how thick I am, that's perfectly okay with me.
Sorry, we do have a 15-minute break scheduled right now, so I don't know if you want to take some questions during the break, we could do that. And if you want to take a break, go take a break, and we'll start. We'll start again in 15 minutes.
Yeah. So, I think most people are happy to take the break. Okay.
No, he has a question. Go ahead, please.
Tell us about your aquarium.
Oh. Well, when I was young, I used to catch fish a lot. And then I started breeding fish. And then I started selling fish to pet shops and that. But I started to notice that the range of fish in the environments was decreasing. And so I started to get worried about it. So myself and my wife felt that you know, by the time we started thinking about the aquarium, the total yield of fish from the oceans had reached a maximum of 100 million tons a year. It's been like that ever since. But the species has been getting lower and lower in the tropic levels. So we set up the aquarium to try and make people aware of what was happening in the environment to the aquatic creatures which people couldn't see. And so when we set it up, we we built it ourselves, we financed it ourselves, and we set it up as an environmental exhibit of what was going on in the world. But we also wanted to learn to breed fish. And so within about 4 years, we actually have bred over 800 species of fish. And at that time, every other aquarium and people breeding fish, their total was only 200. So it wasn't that bad. It also became the biggest tourist attraction, privately owned tourist attraction in Ireland. But we got fed up with it. We didn't want to be tour guides. So we sold it on to the Sea Life Centre. So.
One more question.
Just quick question about the fish. I heard a expert on water give a lecture a couple years ago,
yeah.
And one of the big problems that they have is that even after all the processing of the sewer, etc., that there's so many of the steroids, the contraceptive steroids, that are still coming out.
There was,
and the fish are
yes, but
actually
there was a
suffering.
bigger even problem with nonyl phenol, which is an estrogen stimulator, and that causes problems. But we have been doing research on sustainable aquaculture. So we now have got it to the stage within a system the same size as your bath, we can produce 50 grams or kilograms of fish a year just using the rainwater that lands on the bath. And it's 100% recycling. So nothing goes into it except if you put it in.
Right.
So yeah, we're not just doing climate science and that, we're doing a whole range of research into sustainable aquaculture, into building new improved heat pumps and all that sort of stuff, you know.
Yeah. But my point was that, you know, it's usually blamed on pollution, etc., and people ignore this obvious source of problems.
Yeah. Okay. Oh, another question.
Can you stand a couple more?
Yes.
Yes. My name is Bob Enlick. I'm an operational weather guy.
Yes.
Retired. I know Willie pretty well.
Yes.
So I've got some comments here. We used radiosondes every day in forecasting for Air Force operations.
Yes.
So my first comment is you had a comment that the troposphere is an equilibrium.
Well,
And it's really not.
Hang on. No.
Okay.
Hang on. What I'm saying is it's in thermodynamic equilibrium. The energy potential and so on, it's obeying an equation of state. Around clouds, you do get hotter above the clouds, colder below the clouds, and on a day-to-day basis, you get the entire atmosphere changes as it blows back and forward. So when you're saying it's not in equilibrium, what I think you're actually saying is it's not a constant phenomenon, that there's variations that occur. But I'm saying that all those variations occur within the equation of state, and so thermodynamically it's in equilibrium. So it's does that?
No, because
Okay.
like what happened yesterday, you know, we get the heating and we get thunderstorms.
Yes.
So it's not in equilibrium. We have a source of heat at the surface because the visible radiation comes in and heats.
I'm not arguing with that at all.
Okay.
I can let me give you an example.
Sure.
3 days before I came here, I was sitting in my back garden and there was 4 buzzards circulating up above, and they were screeching as they were going up, and I was watching them, and they were rising all the way up from about 200 meters right up to the clouds, and they didn't move their wings once. So they were going on thermals, right? So what
I'm a glider pilot.
Yes.
I've been to
what I'm saying is,
22,000 feet. Yeah.
I am not arguing with that. I'm saying that's perfectly okay with me. The point that I'm making is the difference between thermodynamic equilibrium and the distribution of how the energy is distributed. That's a different matter. We're looking at the total energy in there. The key point behind it is, in order for the radiative forcing mechanisms that they're using to work, they require it not to be in thermodynamic equilibrium, because over 100 years ago, Einstein and his co-authors showed that if a system was in thermodynamic equilibrium, then it couldn't, it absorbed radiant energy at the same rate as it gave out. So I'm not disputing that wind occurs. I wouldn't go out there yesterday and say the atmosphere isn't changing. What you're saying is the relationship between the different quantities, whether it's kinetic energy, thermal energy, that's varying, but they do so in a way that they still obey the equation of state.
Oh, sure.
So therefore, they're still in thermodynamic equilibrium. Therefore, radiative forcing won't work. And the statement that it's not in thermodynamic equilibrium is still false. Right? Does that answer your question? Are you happy enough?
That's one.
Huh?
That's one.
Yeah, okay.
Okay.
Yeah. Yeah. No. No, it's okay. It's okay. Yeah. I have a lead here for. Oh, okay. Yeah. Okay.
The next thing is when the jet stream is nearby,
Yes.
we get multiple tropopauses,
Yes.
leaved tropopauses, sometimes 2 or 3 tropopauses.
According to the WMO definition. And according to the WMO definition, a lot of those ones that I showed you had multiple tropopauses in them. But that's according to the WMO definition. What I'm saying is, when you look at our new definitions, there is only one tropopause, right?
Oh, I can understand that.
Yeah.
And the data that you have there,
Yeah.
that's not all the data. That's just the data that's coded.
Yeah, hang on. I just want to show you something here. As I'm not disagreeing with you. I'm looking here at the dew point depression. So here it comes down to 0, right? And what you'll find here is if you look at the actual wind speeds, below the wind speeds are quite high, and then they drop off and are quite low at the clouds, and then they start to increase again. When you get to the tropopause, again, we find that the wind speed almost goes to 0. So there are all sorts of phenomena going on there, but they're all housed within the system being in thermodynamic equilibrium, which was the point that I was making. Not that there's different... And the other interesting thing is, if you look above the clouds here, this is ongoing research. I haven't... it's just since you're interested. What I'm finding here is that, if you look at the direction that the wind is coming from below the clouds, and then if you look at it when it's coming above the clouds, it's going in a different direction. So it looks like the wind is almost stopping at the cloud formation, but the air above it is circulating in this way, indicating it's been pulled down, and underneath it's the other way, indicating it's been pulled up.
Like I said, I used to fly gliders.
Yeah, so, and I've watched buzzards.
Yeah, it's fascinating.
It is.
Sometimes you can get the lift in the boundary layer up to the cloud base and actually goes beyond. But we were flying not on instruments, just so out of the clouds. Yeah, but sometimes the air is rising outside the cloud too.
I'll talk to you down there.
Sure.